Alright guys, so today we are going to talk about kinematic equations. We're going to begin our discussion of them. And what I want to show you guys is where these equations come from. Now first of all, as far as kinematic equations go and what they are, these equations describe the motion of an object in terms of position, velocity, acceleration, and or time. So these are going to be the four variables that we are going to see in these four equations. Also, the other kind of restraint we put on this is that we will only consider objects undergoing constant acceleration. So if an object has variable acceleration, two things. First of all, these equations don't work, and we would have to use calculus in order to analyze that motion, and that's beyond the scope of the course. So in this derivation, we're going to start off with a graph, and the graph we're going to start off with is a velocity time graph. So if we have a velocity time graph for an object undergoing constant acceleration, that will look like it will have a straight line, and we'll say it has maybe a positive acceleration, so that line's going to have a positive slope. It'll have some initial velocity, which we'll call v naught, and it's going to go up to some final velocity, which we'll just call v. So that's the graph that would be produced for an object undergoing constant acceleration. And the first thing we're going to look at is the slope of this graph. Now the slope, as we discussed in class, of a velocity time graph is equal to the acceleration that the object is experiencing. The acceleration is the change in velocity over the change in time, and we can say that this would be the final velocity minus the initial velocity over, just drop the delta. If we assume that we start at time equals 0, we can just put, how much time has elapsed there. And this actually gives us our first kinematic equation, because what we do is we rearrange this algebraically, and we would get that the final velocity will be equal to the initial velocity plus the acceleration times the time. So this is our first kinematic equation. I'm just going to call this equation number 1 so I can refer to it more easily later. But really, these equations, there's no specific number assigned to any of these equations. But that's the first equation, and we get that by considering the mathematical expression for the slope of this line. And again, this graph is produced by an object undergoing constant acceleration, so this equation is only good for something where the acceleration is constant. The next equation will also come from this graph, but now instead of looking at the slope, what we will do is we will look at the area under the graph. Again, as we discussed in class, the area under a velocity time graph gives you the displacement that has occurred. So what we'll do is we'll view this area as being a triangle on top of a rectangle. And if we can find an expression for the area of the triangle, and we add that to an expression for the area of the rectangle, we'll have an expression for the displacement that the object undergoes. So I'm going to call displacement delta r. And then looking at this triangle and this rectangle, we know that the area of a triangle is 1/2 base times the height. So we need to find an expression for the base of this triangle, and we see that it's actually the time that has elapsed. So this horizontal line here is equivalent to how much time has elapsed. The vertical, the height of this triangle, is a little bit trickier, but you can see that this total height of the triangle will be this final velocity minus the initial velocity. So for the triangle area, we'll have 1/2 times the height, v minus v naught, times the base t. So that's our triangle. Our rectangle will just be, length times height. So that'll just be our height, v naught, times t. This, in essence, is our second kinematic equation, but let's simplify this a little bit more, just so that it's a little bit neater. So we'll distribute the time through that, plus v naught t, and so what we'll get is 1/2 vt plus 1/2 v naught t, and you could do this a couple ways, but you can just say 1/2 v plus v naught times t. Okay, there's several ways that you could write that, but that is our second kinematic equation. The other two equations that we'll get will involve using equation 1 and subbing in for something in equation, I'm going to call this equation number 2. The first thing we'll do is we want to get an equation that doesn't have time. You don't always know the time that has elapsed in a problem. So what I'll do is I'll use equation number 1 from equation 1. We can see that we can express time as being t is equal to v minus v naught divided by a. So that's just an algebraic. I just took this equation 1 and I rearranged it algebraically a little bit. And now what I'll do is I'll sub this expression for time into the time in equation number 2, and that will give me delta r is equal to 1/2 v plus v naught. Instead of running t, I'm going to write v minus v naught over a. Again, we can simplify that a little bit further. We can say that this is 1/2. I'll put the a down here too, just to make things easier. So v times v, and we'll just multiply these two things together. So we'll get v squared plus, minus v naught plus v naught. So these two will cancel out. Minus v naught squared. This will give us v squared minus v naught squared over 2a is delta r, and this is usually rewritten in a slightly different form. It'll be written as v squared is equal to v naught squared plus 2a delta r. So this is our third kinematic equation, and this is very useful if we don't have time. So just kind of going back a little bit here. Each of these equations serves a certain purpose, and when you work a problem, you'll have to see, what variables are given to you in the problem, and that will help guide you as far as what equation you have to use. For instance, if you know that for equation 1, if you have time, acceleration, and initial velocity, you can use equation 1 to find the final velocity. If, however, you don't know the acceleration, but you know the final, the initial velocity, and the time, and you want displacement, you can use number 2, okay? Because equation 2 doesn't have any acceleration in it. We don't need it for equation 2. As long as we know enough of the other variables, we'll use that one. So as we'll see, later on in the course, which equation we use is pretty much determined by what we're given in the problem. And so in this equation 3, it's really useful if you're not given time in any way, shape, or form in the in the physical situation that you're presented with. All right, so the final equation, we're going to go back to equation 1, and we're not really going to rearrange it. We'll just say v is equal to v naught plus at, and now we're going to sub this velocity and for this expression for velocity in equation 2. So now we're going to get delta r is equal to 1/2 v naught plus at plus v naught. So again, this whole thing is equivalent to v. Okay, multiply that by time, and again, we're just going to do some algebra and rearrange things here. So this will be 1/2 2v naught plus at times t. We can distribute the time through, we can distribute the 1/2 through, so we would get v naught t plus 1/2 at squared. Okay, so let me just rewrite the whole thing, make it sure everyone's sure. So v naught t plus 1/2 acceleration times time squared, and this is our fourth kinematic equation. Okay, so these are the 4 kinematic equations that we'll be using in this course. They're only useful, or they can only be used when the acceleration is constant, and we will choose which equation we have to use for a problem based on what is given to us in the problem. Okay, what variables we're presented with and what variables we need to solve for.